So, thanks for coming, everyone. Today we're going to continue in chapter 9 of the multi-agent book, and we're going to get to the section on agent modeling and joint action learning, which is something that we had discussed in part 1 of the book with tabular problems. And actually, like all of the techniques we're looking at in chapter 9, most all of them are extensions using approximation of things that we had covered earlier in the book. So I thought I would give a little overview of all the different approximation techniques and where they fit into that and what we can expect about how they might perform on different problems. Because a big feature of all these techniques also is, are they actually able to converge to an optimal solution? And like for some types of problems that is not possible. And for a certain class of problem, it may work out just fine. So what I have a few diagrams I've prepared, sort of walk through that. But what I'm showing here first is just what is going to be common across like any technique that we are using. So this is just showing like a diagram of a state. I'm just showing like a grid world because that's a common toy problem in reinforcement learning. But the state could represent any type of problem you're looking at. There's sort of I have like two little, agent cartoons in here. But this is just to show that, this is a state where there's information about both agents that exist in the state. And then something like some policy, I'm assuming, like, let's say we've already trained our agents to behave a certain way. So then whatever the policies are for those agents, they're each going to provide, an individual action. Like in this case, I'm just showing, they're like arrows for directional movement. So then, when we concatenate these actions together, this is like a joint action that then would be provided to the environment. So the environment in this case is just something that is going to take the state and the joint action and then provide an update, right? Like we're looking at always environments where there are these discrete steps that occur from one state to another. So here, the environment just has to update the position of the two agents. So, they move, and then there is a new state that both agents are in and a joint reward that, this, depending on the type of game we're doing, this could be the same value for both agents or, in a general sum game, this, they could be two arbitrary numbers that don't have any connection to each other. But, the reward should indicate something meaningful that is like related to the goal of each individual agent or, the two of them collectively. So then this information about the transition, including the reward, is then going to go into the learning algorithm. And this is going to apply to like any of the learning algorithms we talk about, even the ones that don't, the tabular techniques, the approximation techniques, they're all going to, have to learn from this information about the transition. And here, like the environment, could have a transition, which is probabilistic. So, in this case, it's just straightforward based on the movement, it updates it to a specific position. But, in general, this transition doesn't have to be deterministic. But once we sample it, there's only one outcome that we actually get. But, some learning algorithms could actually make use of all the different probabilities of outcomes, but oftentimes we just sample from this distribution and then get an update. So is that good so far for everyone? Any questions about like the sort of agent environment interface?
Yeah, maybe one just quick question. So usually you're talking about a matrices here, but like how does that translate to like a database? Because
What do
oftentimes,
you I'm sorry, what do you mean by a matrix?
so you're talking about like a state matrix where it has like n by n
Oh,
different
well,
possibilities.
so this is just like a representation of a grid world where there's like a 2 by 2 like position for each agent, but that's just to have a specific example of a state. Like this state could literally be anything. So it's not like this state represents like a matrix per se. It's just that a grid world is just a common type of environment to use because it's easy to see what the different states mean in terms of the position of the agent. But yeah, like this state could be, I mean, yeah, it could literally like be any abstract thing that you could think of.
Oh, right. What I was asking though is more along the lines of like the implementation side. So like usually like in a state diagram like this, you want to have that translate. Most real world data exists in a database. So like what's your thoughts on how to have the various states correspond to like real world data like inside of a database, for example?
Well,
Sorry,
I mean,
that's a
it's
bad
like
question to ask right now.
like your state could literally be like a database, and then like all the values that exist in the database, and then a new state would be the updated, database values like that. There's nothing wrong with that being a state itself. Or you could extract selected, whatever feature information from the database and use that. But yeah, like there's nothing wrong with having, like the state represented by, yeah, an entire collection of information, whether it's, you know a database, no, like, vectors of numbers, symbols. That, yeah, it could be any collection of information that just defines what is needed for the environment to provide a transition. And that's like, I mean, these problems that we approach when we're dealing with any kind of reinforcement learning problem, uh, the environment has to be something with well-defined transition, so that like if you're in a particular state, it understands how to update the state in some way. But what the starting state is and how the update works could be any arbitrary function. It just has to be something with consistent behavior. So there's like some distribution of transition states that would occur regardless of, like, and that distribution would be the same when you have start with the same starting state. So it is like a proper, transition function where like the input output should have the same behavior all the time. Okay. So now I'm gonna what I'm showing here is now what happens, like this part of the sort of the pipeline only happens when we're dealing with approximation, which is like in part 2 of the book, in this chapter 9, we're talking about approximation techniques. So these are functions that have parameters. We like the functions are defined by their parameters, and we can update those parameters to get different behavior out of the functions. Oftentimes we're talking about, neural network functions, but it could be any type of function or approximator that uses parameters. So in order to, use approximation, we usually need to have some sort of feature vector mapping that we're using, because usually like the function approximation we're using is something that requires like a defined shape of the data in some way. Like if it's a neural network, there's going to be some input size to the network. So what I'm showing here is just that we have two agents, and then we have the current state of the environment, and then this state within, when you then need to get behavior out of agents, there's going to be this mapping function which maps the state information to some feature vector for that agent. And there's like, it could be the same feature vector for both agents. It depends on, like if the agents can observe the entire state, you could create a feature vector that sort of represents all the information to the state. But oftentimes with multi-agent learning, we're talking about observations from the environment. So we're allowing the possibility where an agent can only see limited information from the environment. So you could treat that where the environment itself like provides an observation that is unique to each agent, but it's sort of there's not really much of a distinction between that and like your feature vector mapping could do that information masking, where like you're taking the state, and then however this function works for that particular agent, it is, taking just the information available to that agent and, mapping it to this feature vector. And, then these feature vectors are what get passed to all the other, functions that we would use depending on the technique. So far, this is totally agnostic to whatever technique we're using. We're going to have to do this type of mapping regardless. Now, also, like, so far we've only really dealt with like fully observable environments where the whole state is available. But when things are partially observable, like this mapping only represents some of the information from the state, then in general, to be able to solve like any type of problem, we do also need like some history information. So you'll see often in the book, these functions are conditioned on an input which uses like the entire history of states going back like to the start of the episode for each agent, and also the actions that other agents have taken. Like, so all this information may be necessary to solve the problem, but there are plenty of problems that can be solved just with the current state information. But like, to be complete, we do have this notion of the history as well, and this sort of a history information is never needed with single agent learning. The main reason why we may need the history of states and actions is because the agents may need to know about the behavior of other agents in the problem, and they're not going to be able to use that information unless they understand, like, okay, in this past time these agents behaved a certain way, and from that you can tell like how the other agents would be expected to behave in the future, and that might be necessary to actually to have a successful solution to the problem. Okay, so from here I'm gonna show like the initial approach that we use to using this information with approximation to solving problems, and that was a form of independent learning where we just learned action values, which is like similar to what you would do in single agent reinforcement learning. So, going to see if this sort of makes sense. So this is like independent learning, meaning each agent learns on its own with its own observations. It gets its own reward signal from the environment, but it's not directly using information it knows about the other agent. Like, the information about the other agents in the problem will be incorporated through training just by the rewards it gets, but it's not explicitly using that information. So once like we've already discussed how these algorithms are trained, here I'm just showing how these algorithms actually work when they are deployed in an environment. So like these q hat functions that I'm showing here, these techniques will attempt to learn a function for each agent, the action value function. And this is equivalent to like a q function that an agent would learn in single agent learning. But here, each agent is getting its own feature vector input from the environment. It has its own, its own parameters that this function is conditioned on. And then each agent will just output its learned action values in this case. And here, the policy that is being followed here is just the argmax of the action values. So, here it's like this value happens to be the largest for action 4. I mean, how these actions are numbered is arbitrary. Here I'm just saying action 4 is going down. So then each agent will independently spit out its action values, select the argmax, and then that joint action will be sent to the environment in order to to update the state. And during training, the way with independent learning like this, each agent is just trying to maximize its own individual discounted returns. So the algorithms that we looked at that use this, that end up like all the action selection uses these action value functions, is one was the independent DQN. So that's like deep Q learning, but with this multi-agent extension. And then we also had value decomposition networks, or they are trying to learn better action value functions that have properties that have more convergence guarantees, but that occurs during the training process. Once the values have been learned, you end up with the same thing as you have with IDQN, where each agent just has its own action value function. So here, there's like 4 actions for each agent, and independently, each one is just selecting one of those 4 that's being sent to a joint action. So there was a tabular equivalent of this independent learning. And we go back to the textbook. I kind of pulled out this page from chapter 5. So this is from page 99 of chapter 5. And this is for, again, not like once we introduce approximation, there's other problems that can occur. We've lost some guarantees that we have with tabular learning. Or here we're even looking at a case where we're not even looking at a problem with multiple states. This is just like convergence of this independent Q learning with just a single game state, like a game like rock, paper, scissors, or, we looked at, stag hunt, or a bunch of these matrix games that we looked at. And there is some, theoretical work on this where there are these different classes of games, and they're classified by the number of Nash equilibrium that exist and what kind of equilibrium they are, and some other stuff. And what's being shown here is, does this technique converge? Meaning, like, the agents are just trying to do their best independently. Does that actually converge to a solution? And there are cases where it does. Like, this is probably the most straightforward case where there's like one deterministic Nash equilibrium, and a dominant action just means that there's an action that is the best action for an agent regardless of what the other agents do. Like, the challenge in multi-agent learning often is that what is your best action often does depend on other agents' actions in the problem. But if that's not the case, then we have, this is guaranteed to converge here. And then, there's other cases here and there. There's information about what these games are. But the point of this is just that this independent Q learning is not always guaranteed to converge. And actually, these classes of games, if we have like a general stochastic game, like, a grid world thing, or like the level-based foraging environment we've been looking at a lot, then every state of that problem is its own, game in the terminology of game theory, where there's like a different outcome depending on the joint action of all the agents. And like each state could be in a different subclass of this. So like in order for our independent learning to work like consistently, it means that every state of the game probably has to be in one of these subclasses of games that has this convergence guarantee. And you don't like know that ahead of time, because obviously, like, if you have a complicated game, you have no idea what class all the different states are. I mean, you might not even know that until the whole thing converges. So there's definitely cases where independent Q learning will not necessarily work. But one of the examples, actually, wait, let me just go back in the book. So this example, we're going to use it again with approximation, but this was this level-based foraging game in a tabular problem where there's a limited number of states, and we can represent all of them as a discrete thing with its own estimate. So for this game, the agents are trying to collect these items, and they get rewarded for collecting them. And it's basically a cooperative game. Like, some items they have to collaborate to collect, like this one. This one, any one of them could collect. But we can solve this problem by assuming that the agents are just they're both benefiting from the reward from each agent. So it's a fully cooperative task. And in this case, we did solve it with independent Q learning. And central Q learning is a case where you actually like fully turned it into a single agent problem, where now it's like guaranteed to be solvable with just single agent RL techniques. But this task was solvable with independent Q learning, at least in the tabular problem. And because this is a fully cooperative task, it's likely that all the different individual states that you end up in this task are one of those problem classes where independent Q learning works. And you would sort of expect that for a fully cooperative game. Like, usually these other solution problems happen where there's some sort of competitive nature between the agents, where they have a difference of preference between actions. In this case, we would expect, that in all the different states, they should share preferences for actions. Because like when they have to collaborate to collect something, they're only going to benefit if they both choose the action that makes sense to collect it. Otherwise, the outcome would be they can't collect the item, and there wouldn't be any benefit to doing that. Even if we so usually when we have environments where there's not true competition of any sort between the agents, we would expect even this technique to converge, where like probably independent Q learning is the technique that has the most situations where it won't converge. Like if there's some, if your game has the wrong solution class or something. But the reason why this level-based foraging task was one of the examples used is because this is an example of a game that appears to be solvable even with independent Q learning. So does that make sense to everyone? I know like some people probably weren't in the meeting where we went over this task, but we're going to be using it more. But yeah, it's just, this is sort of like the classic grid world problem for multi-agent learning, because you can create situations where the two agents either can collect items on their own or they have to collaborate, so you can sort of test how algorithms are able to successfully learn coordination between the agents. And also you can make the problem harder and harder by having more agents, more items, and make the grid world just larger. So it's a pretty flexible environment. But in this formulation of it, with being cooperative, we had independent Q learning did seem to work on it. That's good. Any questions about this?
Yeah, sure. What's some quick examples of where you might not have convergence? Just how would you kind of estimate that, like on a example, like, or where would you see like easily? I mean, it's obviously sometimes it's easier to spot convergence than divergence.
Well, like there's games where, like here, let's see. No, they say one. I guess the only like hard no in here is class 1B. Uh, but yeah, there were a lot of matrix games examples we had of where these things failed or didn't necessarily work. Let's see. Yeah, so 2B, like this doesn't always converge. Like Prisoner's Dilemma is one of those. Chicken Run, but these were just matrix games where yeah. So in chapter 5 we went over a lot of these, but this is like a game where there's like two different Nash equilibria in the game, and then there's also a probabilistic one. And then this is a case where, again, like when you have an environment with different states, once the problem is solved and it converges, every state will have some sort of game matrix like this. Like this is just for two agents. If there's more than two agents, this is extended in more dimensions. But this is just showing for the joint actions, like for AA, AB, BA, what the reward is. And these values, when we have a stochastic game where there's different states, these are not just the reward values. These also include the expectation of what happens in the future. And really, like when you solve a game with different states, every state of the game could have some game outcome matrix like this that could have any arbitrary values in any spot. So, we looked at some specific game examples where we plotted like where the equilibrium solutions are. Just showed one. I don't know. Like Prisoner's Dilemma is another one where, yeah, I mean that's a very famous game where the Nash equilibrium, there is a single deterministic one that is a bad outcome for both agents. But that's a competitive game.
I'm just reading what AI suggests about this, and it says that AI suggests that the more information that's shared between two multi-agents, the higher the likelihood is for convergence. So when there's little information shared between two
Oh yeah,
agents,
sorry. So
things are
yeah, so
divergent.
this technique I'm talking about is independent learning, right? So in independent learning, there is no information shared uh, between the agents. Like that's why it's independent learning. I mean, the information shared happens completely indirectly. So that, yeah, that's why these techniques can fail. But in contrast to that, if you do full joint action learning, where you're learning, like where you're looking at the whole picture between both agents, then that can converge. Um, yeah, like we already know that's fine, and that can learn this sort of joint action matrix. But yeah, what I was showing, yeah, those cases, those failure cases, the reason why they would fail is, yeah, like there's no information sharing between the agents, and each agent is only using its own uh, action value function. So, but yeah, I mean, if you want to know like the really technical answer of this, I showed this table where like these are the cases where independent learning can and can't work. But again, like you wouldn't know this ahead of time um, with with a stochastic game, right? Because like you don't know what subclass each state is going to end up in. But yeah, by the end, we're going to get to a thing where there is more accounting for the behavior of other agents that can um, improve convergence. Okay. Well, if there's here, I'm gonna move on to this. So this was right, independent value learning, right? Because the goal here is for each agent to learn its these action values. So the next thing we looked at, it's in chapter 9, was a version of policy gradient learning that also was independent learning. So each agent is still um, learning its own policy function where it's trying to maximize its individual returns. Um, so now these, what used to be these action value functions, are now like what this algorithm is going to produce at the end are policy functions. And the policy functions will output a distribution over actions instead of these action values. It's sort of the same shape of the output, but we have independent policy distributions for each agent in each state. And then those agents' behavior will just follow sampling from these distributions. So now, like, there's not just like an argmax in this case. Like here, like let's say, this is the distribution for agent 2. There's of course a probability that it selects the action which is not the most probable action, and that's fine. And actually, this occurring, it could be that like the true equilibrium solution to this problem requires like a stochastic policy like this. It could also be that it hasn't converged yet and it's still learning. And this distribution across actions is what allows it to explore more. And one of the nice things about these techniques is that you don't have to set an explicit like exploration parameter during training, because as long as your learning rate is low enough where you're not, I mean, all these techniques require your learning rate be low enough. Like there's always a chance they won't converge if your learning rate is too high. But if it's low enough, then the policy should update slowly enough that you have a decent amount of exploration during the learning process, just from the distributions not being, super sharp around one action. But, otherwise we get, the joint action is produced. And then the algorithms we had looked at for this in chapter 9 was independent actor critic. That was one. And then centralized actor critic, we still end up with these individual policy functions. It's just that during training, there is more communication between the agents a little more directly, because we have some centralized information shared between the agents that we use during the training process. But once the agents are trained, they have still these individual policy functions that are used. Now, I'm trying to think. So this it's actually the first example in this chapter where we looked again at this level-based foraging problem and looked at performance over time. And it appears as though this actor critic algorithm converges. If this gets close to 1, that means that it the agents have learned to collect both items. And then this is an example of a much a larger, not a larger grid, but 3 agents and 3 items. So there's a lot more, actions to learn from. And it appears to be learning here, although much more slowly than this. So there wasn't any information in the book about actually like how this is guaranteed to converge. But I would guess similar to some of the other policy algorithms that if you see the policies themselves converge, meaning like not necessarily the perform, like here we're showing the performance over time, but also you can look at the policy functions themselves. And if those policies are converging, it's likely that it has found some equilibrium solution because it's directly operating in the policy space. But I'm not actually sure. All I can say for sure is that this does manage to work on this level-based foraging task. But again, this is a task where we wouldn't expect most algorithms to have a problem where they don't converge, right? Because it doesn't inherently have competition. And testing this on a more competitive task could have problems. Like there was a soccer game we looked at, like a zero-sum game, and it's possible that wouldn't learn how to converge to the Nash equilibrium in the problem, but it does appear to work here. Okay. So again, like the policy, this is like very similar to the independent value learning, right? Like the only difference here is that we learn policy functions and then we sample from the distribution. So that's like so far these algorithms are what what we covered in the earlier sections of chapter 9. So the part we're going to get to now, just like this section 9.6, is we're going to go back to looking at joint action learning, which is something that we looked at with tabular methods, and it has a lot more challenges in the world of approximation. Because when we do joint action learning, the idea is that we have this Q function, but now the Q function for a particular agent, instead of just learning its own action values, it's going to attempt to learn values for all of the joint actions. And here, because there's 2 agents and 4 actions each, there are now, 16 of these joint actions, right? And how you actually get the function to output this is a subject of discussion in the chapter, because you could input this, like the feature vector, and spit out all of the joint actions. This approach doesn't scale very well, because if you add more agents and you have environments with more actions than 4, this is growing exponentially, like the size of this space. So really what we need this function to do primarily is this column. If you look at it, you could think of this column as the action values for the agent for its 4 different actions once it thinks the other agent has picked this action. So like if we fix this action from the other agent, we have a get back to the 4 action values, right? And this isn't blowing up exponentially. This column is going to be restricted to the number of actions for the one agent. And then we can just construct the function so that we give it as an input the actions of the other agents. Like here, like this top part here, there's only one other agent in this case, so it's 1 action. But you could imagine if there's more agents in the problem, then there would just be more of these joint actions. And for each one of these, and for the particular state we're in, we have a new set of action values. Okay? Now, the other thing that this technique needs to work is that each agent needs a model of the other agents in the environment. So I haven't said yet how those models are learned, but you can imagine they are attempting to construct a model that predicts what actions the other agents would take in a particular state. And their actual policy function here, where we have a model of the probabilities of the actions the other agents are taking. Because we actually need this model to construct what we ultimately need to select an action, which is we need just the action values for this one agent, just like we had with independent Q-learning. But now, instead of the model itself just learning these four values are actually going to be computed using the joint action values and then the probabilities from the agent models, right? So this first value here is like a weighted sum, right? It's a weighted sum of all of the different values for the up action, but it's being weighted over the probabilities of what all of the other agents do. But we end up combining these two pieces of information into a single, action value vector, and then we select the argmax from that again to produce the joint action. So once we do this computation, this then just proceeds forward the same as when we had just independent Q-learning. It's just that the way we got these action values is different, right? We end up using, we have this function that can do joint action values. And the algorithm, this is going to, we had a tabular version of this with joint action learning with agent modeling. And then the algorithm we're going to, introduce, chapter 9, is the deep learning version of that. And the way this algorithm is going to train agents, instead of just maximizing their return, because when we have joint action learning and we're accounting for the other agent actions, this is called like best response training, where like at any moment, each agent is trying to train all of its functions so that it gets the best response action. And it's a response because it has a model of the other agent's behavior. So it is selecting its actions based on, what it believes the behavior of the other actions will be. And its action is supposed to be the one that does the best, given how the other agents behave. So it is like sort of in its model of everything, imagining how its response to the other agents, how successful that would be. Okay.
Can I ask a question?
Yeah, sure.
So so the trick is how do you combine the learnings of the two different agents, right? And I see you have a weighted sum of joint action values. So what are the weights used in that weighted sum?
The probabilities of the joint action. So we're actually like computing an expected value here. But this algorithm, once it's trained, will have a model of each other agent. So it can use that model to actually either directly compute the probabilities for all the joint actions, or more likely sample from that. So it can use the models of the other agents to say like, hey, give me a sample of a joint action that the other agents would take. And you can collect a number of samples of those. And then you can also use that to compute these action values, right? Because we need to compute an expected value here of our, for every action, but it's going to be an expected value using, what we believe how the other agents will behave. Because like everyone is going to select actions simultaneously here, right? Like all these games, right? There's like simultaneous action selection. So because we don't know what the other agents are going to do, but we can imagine what they'll do. And we have a belief about the likelihood of all those combinations will be.
So is this like ensemble learning? You have like an ensemble of agents and then you basically...
It's not really ensemble. I mean, here the two agents are like the actual two agents that are participating in the environment. But each agent maintains a model of the other agents. I mean, here there's just one, but let's say you had 10 agents. Then each individual agent would have a model of the 9 other agents. But again, those are just models. So that, I mean, the only reason it needs the models is it needs a way of translating this joint action space, right? Which is like, this alone doesn't tell you what to do. This only tells you what to do in the context of a model of what the other agents are going to do. Because you can look at this and be like, oh, like Q2 is higher than all the others. So it's like, well, that's great. Like, so if the other agent does this, then like action 2 would be the best. But you don't know what the other agent is going to do, right? But if you have a belief about what the other agent's going to do, then you can see, okay, well, given that it's likely to do this, but there's also some chance of it doing this as well, then you can build like a composite action value.
Okay.
Off of that. But we can look at the book and get a little more concrete about how this works with agent modeling. So just to remind people, and there is a video of these older meetings too, if you want to look, but we had looked at, let's see, where is it? Joint action learning. Oh, here we go. So this is what we looked at in chapter 6, right? And this was with tabular learning, but here we had joint action learning with agent modeling. And it was the same idea, just without, approximation functions. Here we're just using tables. Like here, these inputs are just, there's like a distinct value for each input because it's a tabular problem. But same exact idea where there's this function here, this action value function, where here we're computing the action values using the joint action value function and the model of the other agents, right, to produce a single, action value function just for one agent, right? This is the joint action value function, you could see, because it doesn't just depend on the actions of one agent, it also depends on the actions of all of the other agents. That's the notation this book uses is this minus I for the actions of all the other agents.
I guess the question I want to, on the back of my mind, is let's say there's 10 agents and 10 of them are independently learning how to solve a maze. Why not choose one, let's say a coordinator that aggregates over the learnings of each of those 10 to come up with some joint distribution versus like each of them learning all the remaining other 9, which is like a square kind of problem, right?
In that case, I don't know how that maze problem would be translated into a so what is the goal? I mean, if the goal is for each of them to exit the maze, then they could each just learn independently, and they're like, that's not a task where any coordination is required, right? But okay, so if you have a bunch of agents and they have a shared goal, then you can turn that into a single agent problem, because you can take the reward signal, and let's say, like, if there's truly a shared goal, then you can produce a single reward signal where there's like a common goal among the agents. Then you can learn with a single coordinating agent that learns across the joint action space of all the agents. So and we talked about that, and again, I'm sorry if you weren't there, but like this was one of the things we covered in an earlier chapter, where that's like a central learning reduction of the problem.
Okay.
And that you can solve with single agent learning techniques, because where you take, I mean, I can actually show in the notebook I have one of this level-based foraging task. I have that as an example where you can turn it into a single agent problem and you can solve it that way. And then you don't have any of these challenges with multi-agent stuff. But you can only do that in a problem where you can take the reward and turn it into like a single value. So it's fine if you have a totally cooperative task. If you have any kind of, like, again, competition, it doesn't work because there's not a trivial way.
Okay, I see now.
You can do that. But the reason why you might not want to do that is because of this joint action space problem. If you have 10 agents, each of them have 4 actions, then you have 4 to the 10 joint actions, right? And that is way too big an action space to learn in, right?
Okay, so I'm imagining a multiplayer game now. So there's a multiplayer game. Each of them is trying to win. Let's say a game of conquest that comes to mind. They're trying to, model the other agents and what their strategies are to come up. Like,
you mean they're competing?
They're competing. Yes, they're competing essentially. So in that scenario, then yes, you need to have a model of what the other people are doing.
If they're competing now, well, like I said, so you have convergence problems, even possibly with cooperation. If you have competition, you have a lot more to worry about because now you're talking about, like, let's say it's a zero sum game, right? Then you would try to hopefully learn like the minimax solution, and we cover that also in an earlier chapter. But there are lots of techniques like this that will not converge to the minimax solution. Like independent learning usually won't. This joint action learning has a chance of converging to that, or like a better chance of that working.
Okay.
But independent Q learning, like what we just talked about, that's not going to find a minimax solution in a competitive game.
Yeah, I think that makes sense. I guess what I'm still struggling with is that a scenario where you have multiple cooperating agents, but you still don't have one single objective function for them all. Because if they're
Oh yeah, that's
cooperating,
yeah. So
what?
that is like this level based foraging task. Actually, you can set it up where yeah, they each get their own reward. So like there are some items that one agent could collect, and then only that agent
Oh,
will get
okay.
a reward. There's others where they would share the reward from collecting both, or you know, like mixing and matching. So yeah, that is we'll call like a general sum game where each agent has its own reward, and general sum meaning like there could be certain situations where there's competition and others where there's cooperation, and it's just like a mixed bag. Just each
Got
agent.
it. Okay.
But again, that's a complicated game. And if you do independent learning, it would not be guaranteed to converge in that case, because to truly get a solution to that, you need like full joint action learning with like you have to use a game theory concept, which you can get from agent modeling. But yeah, this sort of agent modeling approach is probably the only simple way that that would have a chance of finding different equilibrium solutions.
Okay.
Yeah, but I don't know. Well, it might be easier if we get it a little more concrete here.
No, that was helpful. So basically, different types of games end up requiring different strategies, and to get them to converge, you need to be careful as to what strategy you
Well,
choose.
yeah, I know there's a lot of problems. I mean, we already covered this in the tabular learning, but even like forget approximation, forget like neural networks, even just even forget stochastic games. Like just take a simple matrix game where there's just one state. Um, Even that there's not a straightforward way to get the equilibrium solution there. I mean, if you just have like general sum game, like finding a Nash equilibrium is like an NP hard problem. So some of these techniques, if they converge, will converge to an equilibrium. But that doesn't mean they will converge. It just means that they're not going to converge to something that isn't an equilibrium. But, it doesn't mean they actually will converge. So,
Okay.
I mean, and that's in the simplest case of this, right? Like we keep making the problems more and more complicated with like multiple states, larger state spaces, all that stuff. But I mean, this book is actually like pretty light on its discussion of like theoretical convergence of things. I think probably because a lot of those questions don't even have an answer now. Because like a lot of these, like you can get an answer like in this particular class of problem under these restrictions, this technique will converge. But then in any kind of real problem, none of those assumptions are true. So I just think that there's a lack of theoretical understanding of when these techniques will work. You can always just test them and see if it works, which is what we end up doing in a lot of this chapter. But I would say like if you're concerned that there doesn't seem to be a straightforward answer to a lot of this about like what technique will work, when will it work, like what should I use instead, there isn't a clear answer for, like this subject matter is a lot less mature than reinforcement learning, and there's just a lot of theoretical questions that don't have an answer right now. But maybe that'll improve in the future, but for now all we can do is sort of test things and see how they work, which I was gonna like here. I'll just show quickly an example of this. This is a chart from later in the chapter. Okay, this chapter also it shows this. It kind of goes back and it continues to come back to this problem, this level-based foraging problem. There's lots of versions of it. This looks like a very small version of the problem. They've added this caveat here that every item needs cooperation to solve. You can instantiate this problem where some of the items won't need cooperation, right? Those items are going to be much easier to collect or to learn. So in fact, if you make the problem where every item requires coordination, it's probably a better test problem. Because otherwise you can't tell if you're training it, if it's only working because one agent is learning to collect one item, which is just a single agent problem. Here you can sort of see you're really testing, like, these agents have to work together to get this to work. And here they show that IDQN, which is, that independent value learning method, doesn't work, right? This is a small problem. Now, we know that in the earlier part of the book, in that example, where one of the items, right, did need coordination to collect it, independent Q learning did work. So here they're making this point because they're trying to compare it to this agent modeling approach that does work. They're saying, look, IDQN doesn't work, but the joint action learning with agent modeling does work. But we already know that IDQN probably should work in this task, like, because of the nature of the task and the cooperative nature of the task. So obviously, like, when you're dealing with approximation and learning rates and hyperparameters, maybe this technique just has a really hard time converging and finding the solution. But it doesn't necessarily mean that this will always fail. And actually, when I was training this and testing it, I found that IDQN was able to succeed in some of these problems, but exactly why it's failing is a little hard to tell. I mean, we can look at some of those examples in a second. So yeah, like, even in the context, yeah, like here, right, like this was like from chapter 6 of the book, where it shows all of these techniques work eventually. They're just saying that the agent modeling works faster, maybe. I mean, this is also cherry picked for the book. Like, it's possible you could find hyperparameters that cause this to converge just as fast. And by the way, the CQL, that's like the approach where you completely turn it into a single agent problem, where you have like a centralized controller that is directing the behavior of all the agents. So this problem is small enough that this technique works. So, I don't, like, why would IQL work here and fail here? It could just because it's approximation, although this is small enough that the approximation function should not, if it's complicated enough, you shouldn't have the problem of the approximation function, like, not being good enough to solve this. So I don't know. I would guess this is probably just them trying to make a case for the agent modeling being more valuable. But, or I would probably ask, if I had time, I would like email the authors and ask them, like, are you saying IDQN actually can't succeed on this task? Or was it just like, is the point just that it doesn't converge as easily? Which may be, what they're claiming. But again, it's hard to tell because there's not an explicit discussion of that in the chapter.
Yeah, no, good elaboration. Ideally, you would have some characterization of this game space and parameterization of the algorithms and have some theoretical basis, some theory behind what applies where. But in the absence of that, you have some empirical results which illustrate
Well, there is
where
some
convergence happens.
theory. Yeah. So there is some theory. And actually, before I get into the details of how this agent modeling works, so in chapter 6, this is actually the theory that with agent modeling and how it works. So if the actions converge, so this is like if you're doing this and the actions converge, meaning like when you repeatedly visit a state, if the other agents end up behaving the way you've modeled them, and that doesn't change, then the actions have converged, and then you have found a Nash equilibrium. So that's good. Also, if everything's in a Nash equilibrium, it won't leave from that, so you can keep training it, and it won't break that. Now, the other thing you do, like, this is more, I guess, akin to the agent models. If the empirical distribution of each agent's actions converges, So this is like a little more like we had in the tabular case where we're actually counting the actions and we're averaging the actions over time. And in that case, because there are cases where in any given step, the agent model will actually, or not the agent model, like what the other agents do will switch. Like there's in the rock paper, if you do this with the rock paper scissor game, a game everyone knows, you end up where the agents keep switching their actions. So they keep switching from selecting rock every time to paper every time to scissors every time, and both agents keep switching. Now, if you look at their switching, it turns out they select all the actions with 1/3 probability. But that's not the same as on any given step, each agent will select, each action with 1/3 probability, right? That's like the true equilibrium for that game is for that random selection to occur. But it might not actually happen that way. It may just be that if you observe their behavior over time, the actions keep changing to match that probability. So either the actions themselves on a given step will match the true equilibrium solution, or if you observe the actions over time, then and you sort of, either, well, in the modeling case, we're going to have a neural network model what we think their policy function is. Then in that case, right, if that sort of empirical like observation of their behavior converges, then that's also a Nash equilibrium. So that's good. It doesn't mean it will, but again, like this doesn't mean it will converge, right? It just means that if it converges, it's converged to something good, or the equilibrium if that's what you want to achieve. So this is something. Of course, this doesn't apply to the thing chapter 9 because now we're dealing with a nonlinear approximation and everything. But this is sort of like the best case scenario. We can. And there's also no discussion of this convergence in chapter 9, so I thought I would just throw in this reminder of what we previously had about agent modeling. But at least in the level-based foraging game, this the actions do converge, and you could see it in also other simpler games. Like we tested this with all the other like 2x2 matrix games, and it the empirical, those games usually we have this converging. Yeah, the empirical distribution. So we're gonna now talk a little bit about how this works in the case of approximation. So yeah, the agents are going to learn, like I already mentioned this centralized action value function that will depend on the actions of all agents, right? So because it's a joint action value function. And then they need to know the actions of the other agents, but obviously there's no way of knowing that ahead of time. So the best other thing we can do is we can learn a model of the other agents and use that to compute this thing here, which is what we need, right? This action value function is what we have when we do independent Q-learning, but here we have to construct it. And the way we're constructing it, just like in the tabular case, is we take this weighted sum over the probability models of the other agents and using what is our joint action value function. Now, this loss function, this is the same thing we had with independent Q-learning, actually. This is just trying to, this is the loss function you also see in regular reinforcement learning, where each agent is just trying to learn their proper action value function. The only difference here is that here we have to put in the actual, this is occurring on data we've already observed from like an episode. So here we have the information for these previous, steps. We have like this history buffer here. I'll just show it here, right? Where as this training loop is going, we're going to collect, store. Yeah. So we're storing these transitions in replay buffers, right? So we have, this is like the observation history of that one agent, the actions, and then the reward it got and the next state. But later we're going to sample from this and get, we're going to use this information that we've collected. So because we've collected it, we have the information about what actions were actually taken by all of the agents. So we can plug that into this function as an input, and we have also the action that our agent took. And then this maximization over the action value, this is just the same thing we do. This is like the bootstrap estimate of the value, right? So we're comparing like our joint action value function. This is like we're trying to minimize the squared error loss with our action value function, and this estimate of what it should be. This is like the one-step bootstrap estimate we often use in reinforcement learning, where we use the reward signal, and then the action value function at the next step, which in order to compute this, we have to also compute this action value function again, which obviously this is a lot more computationally intensive than when we just do independent Q-learning. Because like this always involves multiple computations of this function. Now, this sum, right, is computing an expected value, and it's summing over all of the joint actions of the other agents. And if we really do that, we have a lot of scaling problems, right? Because we already are trying to avoid dealing with the full joint action space because it's going to blow up exponentially. But there's a nice trick you can use here, which is shown in this equation here, 9.84. And here, all we have to do is have a way of sampling the actions of the other agents. And this is what I mentioned this briefly when I was showing the page in the notebook with the diagram, where we have to take this weighted sum of our Q function, right? But instead of actually weighting it by these probabilities, we can just take a sum of samples of it, where we're sampling now different values of this, right? Where these are the actions of the other agents. And in order to sample from this, it's not too hard. All we have to do is we have the models of the other agents, and we just have to use those models, then spit out a sampled action from each one individually, and then we have a sample of the joint action, right, of the other agents based on their models. So this is not too computationally hard to actually collect a number of these samples, right? Does that make sense to everyone? Like we have, each agent is going to have a model of the other agents, and it can use those models to just go one at a time through them, say, okay, agent one, what action do you want to take? Agent two, and then it just collects, and it can just repeat that k times through all the agents, and then it can use that to take sums of its joint action value function. Again, to avoid this blow up of the space, right, we're actually using the action of the other agents as input to this function, rather than forcing this function to output, you know, whatever it would be, like hundreds of values at a time. It only has to output the values for a single agent, which is what, yeah, I'll go back to here, but it's what I'm showing here, where instead of outputting all of these at once, right, it's just going to output the one column of values conditioned on this input, whether it's one here because there's only one other agent. But imagine there was a lot of other agents, then you would just have a collection of the other actions, the actions of the other agents. So the hard part of this is like actually computing the action values requires these models, but training the models themselves is very straightforward. Because, I mean, actually, if you do supervised learning, right, all we're doing with the model training is we're observing the actions the other agents took. We're just using that as a data set, and we're just minimizing the cross-entropy loss. So just like we would where we're training, a probability, like a classification function. Here, instead of classes, like the classes are the actions taken, and we're just trying to match that probability from the other agents. So here, like we grab for in the replay buffer for the states we saw, and then we're trying to match our functions to accurately reproduce the actions taken by the other agents. That part is probably would be the most familiar to people, is how, I don't know if I guess it's only written out. I don't know, here it's written out too, but yeah, it's this loss function here. right? But this is exactly the same as what you do with like, supervised learning training a classifier, where here the classification labels are the actions that each agent is taking. Now, technically, the way they describe this is that each agent has a model of all the other agents. And so there's like going to be like n minus 1 distinct models of every agent. That is a lot of parameters and a lot of things to train, but the reason why we need to do it that way is because the model of the other agents can only depend on what our one agent sees, right? Because like, well, once we deploy this, we have one agent, it's going to get information from the environment. It has to take that information and use it to represent a model of like of the other agents. Now, even though those other agents may have a better model of their own behavior because they have their own input data, the agent we care about doesn't have access to that data. So the input used to these models is going to potentially be different for every distinct agent. And that's why you have these parameters indexed by two different indices, right? This is like the model from agent I of agent J. So we'll get later, there's later sections of the book where we talk about sharing parameters and having homogeneous agents. But if we don't have that, we then potentially have quite a lot of these parameters to worry about. I believe when they show training examples here, I don't know if they say if the parameters are shared between agents here, but it is something that we get to later in the chapter. But yeah, so are there any questions about this actually dealing with the approximation here? Okay, I might, so for now, I think I might want to show like some of the equivalent things I talked about, but in like an actual concrete example here. So here I have like an implementation of this level-based foraging task, right? So here's the task. Now, I didn't include it in the notebook, but right, the agents can move and then they can collect an item, or like the no op action is just they do nothing. So there's a few extra actions here. But so this is the environment, and this particular version of the task, right? The grid is pretty small, but it's constructed so that every item requires coordination between the agents. Like here, they can only collect an item if their level sum exceeds or is equal to or exceeds the item level. So here, like the item level is shown in orange and the agent's level is in blue. So here you can see that like both right items require both agents to collect it. So the way this like the episode ends when both items have been collected. So here we have like the initial state. The way whenever you initialize a state, it'll randomly position the agents and items in the environment. And here I'm showing the transition that occurs. So this is showing an initial state we start with. Then the up action is taken by both agents. They get a reward of 0. Sorry, the text formatting isn't great here, but I didn't have time to play around with it. And then this is the state they end up in. So obviously both agents go up and they end up in this position, right? Very similar to the diagram I drew. And the reward is 0 because nothing has been collected in this case. So that good, makes sense. So next thing I talked about was the feature vector mapping. So here I have another initial state to deal with. So I had like, you're free to choose whatever kind of mapping you want. So you can test different examples with this problem. This is a dense feature map that you can use. The way this works is it just maps the X and Y position of both agents and both items as like a value, and it's normalized to between -1 and 1. So yeah, like here, this is like the X position of agent 1 is 0.5, I think. Yeah, so 0 would be like in the middle. Yeah, -0.5 would be, I guess, far left in this case. And then the item levels are also normalized to a value. So this is like no attempt here to like everything here is a numerical value. And again, this type of feature map would probably be very difficult to learn from, because especially with the item levels, it's like you're representing them as just like a real number. And then the function is going to have to like understand how to compare the real numbers and get greater than or less than, where really it's more like, I mean, there is a ranking in that case, but same with the positions. Like we have this XY position, but it might have an easier time learning if we instead tell it like, well, this is really like X position 1 of 4 in the X direction. And that would be more like a sparse encoding, which I have here. So in this case, like, because I'm mapping all of the state information to this dense vector, this would be a case where you could give both agents like the same feature vector, because there's no relative positioning here. Like I'm saying like the explicit position of everything to both agents. This is an example of having a feature vector map where the feature vector is relative to that agent. So it represents the position and the normalized level of the other agent and the other items in the problem, like relative to this agent. So I would say like this is like a 2y, and it shares the same X position as this item. And also it's like a sparse encoding of the position. So here, like negative means it's to the left or below if it's the X or Y direction. And then the reason why there's all these 0 values here is because I basically like have a one-hot encoding of where it is in the relative position. So here there's like 1, 2, 3 potential relative X positions that it could flag, and same with the Y direction. So this is just a little more sparse encoding, probably better for something like a neural network to learn from. So this is showing like the actual mapping of this state into these feature vectors. So now this is an example of an IDQN solution that we can see here. So this is the sum of the reward over an episode. So here, if you go back up here, here's some examples of training IDQN on this task. So here's a training run, and it ends with this reward performance of 0.34. Now, if it succeeds at everything, it should be 1, right? So 0.34, clearly this is not like entirely successful. Again, it may just need like more training time. It's a little unclear unless I do more testing. Again, this is also the harder task where both items require coordination between the agents. But we can see an example of this solution and what it looks like. So we have the initial state here. And then this is actually like what the learning, like the training algorithm has learned from this. So right, we have, these are the action values. Right, so there's 6 action values for each agent. They each have their own independent action values. And then the maximizing action is the one they'll follow, although here I've set it up where they could follow, they actually take random actions with a probability of 5%, which, because the way this was trained, the exploration parameter I used at the end was 0.05 rather than a higher value. So here we can see this value of 0.5 means that this had some success here. So we can see like an example of what it does in this episode. And again, it doesn't have infinite time to do this. So the way the book does it is they just terminate the episode after 25 steps. I set it up a little differently where there's a probability of the episode ending on every step, like a 1% chance. So it ends up creating a distribution of lengths of the episode, but it sort of matches the discount rate of 0.99 that I used in the problem. But it makes sure the agents are incentivized to collect the items quickly, because otherwise there's always a chance that the episode will end and therefore prevent you from collecting the items in the future. We can see how this goes, and I believe in this case they end up collecting. So here, like we can see agents 1 and 2 surrounding this item and then collecting it. And then after that, they don't know what to do. So again, who knows, IDQN, but the fact that it learned to collect this one item means something positive, but for some reason it has trouble, and you can see that from the learning curve and the value of 0.34 or so, that it seems to have trouble once it's collected the first item actually learning how to go and collect the second item. But also, this also matches though the book explanation here of how they said, well, IDQN failed on this task where they have to coordinate. So yeah, it does appear to have trouble learning in this context. Okay, so that's IDQN. We could see what the policy gradient solution looks like. So here, this was a case where this is like using independent actor critic learning. Here's like the learning curve of this. And like, yeah, this didn't even train for very long. So this success rate means it basically learned how to solve the task. I don't know what the optimal solution is actually, because there is that probability of termination on every step, so you can't actually get a value of 1. But, over 0.9 is still good. This is using one type of encoding, feature vector encoding. I also showed, and this is a solution using that relative encoding I showed, where each agent gets like the relative position information. Again, it's probably, you're sort of taking some of the work out of the agent's hands by pre-computing that stuff. And we can see this guy seemed to have an easier time getting a higher success rate. This is showing like the cumulative reward over training. So the slope of this line is like how successful it is. So once this line hits like this constant slope around here, it's just collecting reward at a given pace in the problem. So the solution I'm showing here is that, here is from that relative positional encoding solution. Okay, so here I'm just using the function that samples actions from the policy functions that have been learned. And so we can see it looks like it completed the episode in 13 steps, collecting both items. So I noticed when I was looking at this, so down here, so this is the state of the problem. And then here it's showing the policy function, or like the actual distribution output. And you could see that because these values are all close to 0, so it's basically learned like a deterministic policy, which makes sense for this problem. The optimal policy should be deterministic here, where like this is the optimal action with like, close to 100% probability. So we can see that now if you just look at this, they should collect this item, right? Because they're close to it. But weirdly, the solution this learned is that they go up together. Also, like there is something somewhat smart about this. Well, I guess not, because yeah, like this should already be moving as well. So they sort of make their way up to the top, like too slowly, and collect that item, and then they go down together, and finish up by collecting this item. So I tried another episode where they kind of did the same thing, and they actually leave the closer item first and then come back to it. I am not sure why. It's possible that it just needs more time to converge, or that for some reason in the training process it was easier to learn to move to the farther away item. It could also be an artifact of how big the neural network is, what it could learn successfully. But clearly it understands how to coordinate in different parts of the grid. And if I had, I haven't completed it yet, but if I had completed this with the joint action method, then you could see the same thing, but then this output would be like the joint action. It would actually be more similar to this, where there's an action value output on every step, but there would also be an agent model associated with the other agents. And in fact, once you deploy this, well, yeah, like you could pull out the agent model. Like you could also do this joint action training and have each individual agent also learn its own agent model just empirically. And then you could use that empirical model when you deploy it instead of needing to actually compute the action values. Because like this whole action value calculation here is like needed when you're doing training to update this. You need a combination of this and the policy functions. But you could also like train a policy function for each agent that uses that agent's information. And it would be sort of like learning the empirical distribution of the agent like we did before. And then you could deploy it just with that empirical policy function rather than needing to do this whole, argmax of this thing every time, which is a lot more computationally intensive, right? Because like when you're doing this, in fact, whenever you're doing any kind of learning loop like this, you could use a neural network to learn just an empirical distribution of what the agent is doing. And then if it's performing well and that empirical function has converged, then right, it should like follow the same policy when you deploy it, which is, something optimal anyway. So yeah. Oh, also in this, I wanted to show, so for independent actor critic, also train this on, oh yeah, so this is task 1. So this task is the one with the larger grid and one that requires coordination. I believe if you look at the book, it's a little later. Oh yeah, they have this. So actually, this problem is the same as the one I just showed. This is jumping ahead a little, but we talked about this actor critic algorithm. So when they train this actor critic algorithm here, this means it is learning to coordinate to some extent because every item here requires coordination, just like the one I showed. But it's a pretty low convergence anyway. Also, this is 10 to the 8. So this is like over 10 million. Or no, is this 100 million training steps? Almost, right? One times. Yeah, this is like a lot of training steps that this is operating over. So I don't know why that performs so bad. Like this is like the same exact task, but not training for very nearly as long. Like this is like, I don't know, 11, I don't know, some like maybe 10 to 20 million training steps. And it seemed to learn almost optimal behavior. Like this is like 0.9 instead of the like 0.4. Pretty early in the process. So I'm not sure why, but like all these curves and things in the book really depend on exactly how you set up the feature vectors and all the hyperparameters and everything else. But yeah, this is just regular, actor critic learning. And yeah, like here's an episode run on this where, collected both items. So I don't know. But yeah, next time we can talk about, there's another little interesting thing about this with instead of just learning a model for each agent, there's an idea of learning some sort of compact representation that distills information about the other agent's behavior and using that. So I think we'll save that discussion for next time. And then we can also talk about parameter sharing and homogeneous agents, which is just sort of an extension of this where we have an opportunity to simplify the training process a bit. And we don't need to like have so many distinct parameter sets for all the different agents and models. So I hope, does that sound good to everyone? Like moving on to this, yeah, 6.2 and then 9.7. And then, yeah, if there's anything anyone would like me to show again or from, yeah, either the textbook or the notebooks, let me know. Any follow-up questions. And yeah, otherwise we'll just see everyone next time. Okay, sounds good. Well, yeah, thanks for coming, everyone. And yeah, hope you found it helpful.